Welcome to Chemistry Clips. You are watching amines Part 1. This is a short clip on the preparation of amines. In this clip, we'll be focusing on 5 key synthetic routes. At the end of this clip, you should be able to understand and draw mechanisms to convert organic compounds such as carbonyl compounds and alkyl and acyl halides to amines. You will also be expected to know the limitations of each of the methods we'll discuss. Are they viable? Do they give a good yield? As well as be able to identify or propose the amine product formed from each reaction. Is replaced with alkyl groups. Recall from earlier CH1002 lessons, amines are categorized based on the number of hydrogen atoms replaced. In primary amines, e.g. methylamine, just one hydrogen atom has been replaced. In secondary amines, e.g. diethylamine, 2 have been replaced. And in tertiary amines, e.g. trimethylamine, all 3 hydrogens have been replaced. There are a number of ways in which the different categories of amines can be synthesized, but in this clip we'll be looking specifically at preparing amines via the reaction of ammonia with alkyl halides, reduction of azides, the Gabriel-amine synthesis, reduction of nitriles and amides, and the Hofmann and Curtius rearrangements. Exclusively. Let's look at the mechanism. The azide anion attacks the carbon attached to the halogen. So here, the azide attacks the carbon attached to the bromine, kicking out bromine. This gives the azide intermediate, which is then reduced to the amine with nitrogen gas as a byproduct. Another way to convert an alkyl halide to an amine is the Gabriel-amine synthesis. This method goes via a nucleophilic substitution reaction followed by hydrolysis. Phthalimide is used as an organic reagent, as well as a strong such as potassium hydroxide and ethanol. Sodium hydroxide and water are then used for the hydrolysis reaction. Let's work through the mechanism. In the first step, the hydroxide ion of potassium hydroxide deprotonates phthalimide to give potassium phthalimide, which is more nucleophilic. The phthalimide anion then attacks the 1-chloropropane, kicking out the chlorine atom to give an N-propyl phthalimide. This is then hydrolyzed to give 1-aminopropane and the 1,2-benzene dicarboxylate.
Alkyl halides can be converted into primary alkyl amines with 1 extra carbon atom by undergoing a biomolecular nucleophilic substitution reaction in the presence of sodium cyanide, followed by reduction, The cyanide ion from sodium cyanide is electron-rich. Therefore, it acts as a nucleophile and attacks the electron-deficient carbon center of the alkyl halide. By doing so, it forms a bond whilst expelling the halide ion. So the halide acts as a leaving group, leaving us with a nitrile compound. The nitrile compound is then reduced by lithium aluminium hydride, producing a primary amine with one extra carbon atom. Amides are derived from carboxylic acids and their derivatives. Amides are ordinarily prepared by reacting acid chlorides with ammonia, or amines. The amide is then reduced by lithium aluminium hydride, producing a primary amine. Note that the amide reduction converts carboxylic acids and their derivatives into amines with the same number of carbon atoms. The Hofmann and Curtius rearrangements are reactions which convert carboxylic acid derivatives into primary amines, with a loss of one carbon atom. The Hofmann rearrangement is a reaction where a primary amine is formed from a primary amide. The mechanism to this reaction may look complicated, but you should be familiar with each step, as you most likely would have studied them previously. In this reaction, the base abstracts an acidic amide proton, forming an amide anion, which then reacts with bromine, forming a bromoamide. The final amide proton is abstracted by a base, producing a resonance-stabilized bromoamide anion. As you can see, the R group on the carbon moves to the nitrogen as a bromide ion leaves, forming isocyanate. By adding water to isocyanate, nucleophilic addition occurs, forming carbonic acid. Carbonic acid loses carbon dioxide spontaneously to give an amine. Followed by a spontaneous loss of a leaving group, which then forms a primary amine. In both reactions, the primary amine product has one fewer carbon atom than it started with. The key difference between these two rearrangements is that the Hofmann rearrangement starts with an amide, whereas the Curtius rearrangement involves an acyl azide. After viewing this clip, you should now be able to draw the mechanisms for the conversion of alkyl halides and carbonyl compounds into amines. You should also be able to identify or propose the amine products formed from the various reaction pathways.